With each captivating picture from the James Webb Space Telescope, it continues to gather thoughts from various corners of the universe, including planets within our own planetary framework. A year earlier, we pondered our initial brief glance at images showing the Carina Nebula, Stephan's Quintet, and, strikingly, the mesmerizing Deep Field image. This particular picture apparently portrays various galaxies stretching out into the vast expanse of the universe, fulfilling the hope sparked by the James Webb Space Telescope. It hasn't stopped to astonish. It has recently revealed objects that challenge established cosmological theories. These confounding discoveries are now marked as universe breakers by cosmologists, perplexing mainstream scientists with their ability to conflict with existing concepts. The reasons for these revelations remain cloaked in mystery, throwing our estimates and theories into disarray. So, what's the latest scoop from the James Webb Telescope? What incredible, prominent information has it uncovered that was previously unknown to us? Join us as we delve into the revelations suggesting the presence of another universe, challenging the conventional understanding of the Big Bang. Our universe, as we have long understood, arose from a hotter, denser, and more uniform state, a concept known as the hot Big Bang. This theory, a significant scientific achievement of the last century, found remarkable support during the 1960s with the discovery of the cosmic microwave background, a remnant from the early hot and dense state. Over the years, the Big Bang has remained the prevailing theory explaining our cosmic origins. However, new and critical observations have led cosmologists and astrophysicists to continuously question both cosmic expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, reinforcing the enduring nature of the theory of the universe's origin. According to the dominant perspective, the description of the universe's beginning involves a smaller, denser universe in the distant past. The presence of radiation, like photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, density, temperature, and energy levels arrive at a point where a singularity could form and the known laws of physics break down, at around 10 to the power of minus 43 seconds. During that brief time, small distances, short durations, and high energy scales challenge our comprehension. Rewinding the cosmic clock to the hypothetical zero at the beginning, a complex historical cycle would be expected. If the universe began as hot and dense, tremendous amounts of particles and antiparticles would have been created, with surplus particles annihilated by radiation as temperatures dropped. The breakdown of the electroweak and Higgs symmetries leads to the four fundamental forces and particles with non-zero masses. As the universe cools further, protons and neutrons form composite particles called quarks and gluons. The combination of protons and neutrons results in the creation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions experienced growth due to radiation pressure followed by gravitational collapse, leading to the formation of large-scale structures. Approximately 380,000 years after the Big Bang, the universe cools sufficiently for stable neutral atoms to form, marking a critical step where photons decouple, with frequencies increasing as the universe expands. The discovery of the cosmic microwave background years ago solidified the theory of the primordial cosmic explosion as the most supported explanation for the universe's creation. While most astronomers and astrophysicists embrace the Big Bang, ardent proponents of the steady-state theory, like Fred Hoyle, continue to defend increasingly implausible claims, only to face defeat against overwhelming evidence. The proof presented was unequivocal. It wasn't blurring starlight, nor was it reflected or emitted heat from dust. Every conceivable explanation fell short. The galactic spectrum showed astonishing consistency all around, resembling an ideal black body, yet it had no connection to known objects in the universe. Regardless, Hoyle and his followers continued obstructing scientific progress by supporting tentatively shaky choices, even as mainstream scientists moved toward the Big Bang as the consensus. The skeptics lost ground, their flawed efforts fading into obscurity. Meanwhile, the fields of space science and astrophysics experienced remarkable growth from the 1960s through the 2000s, with cosmology seeing particularly significant expansion during this period. We mapped the vast universe and described its structure on a grand scale, delving into the development and dynamic interactions of galaxies and their stellar populations. However, despite these advancements, we encountered anomalies that defied explanation within the framework of the Big Bang Theory. Observations uncovered discrepancies that challenged the predictive power of the Big Bang model, most notably the absence of exotic relics predicted by the theory, such as magnetic monopoles or particles from grand unification. The universe we see today appears to require forces beyond our current understanding, yet these remain elusive. At its inception, the universe required an exact rate of expansion to balance the total energy density, a feat that the Big Bang Theory struggles to justify. Achieving firm equilibrium or sufficient time for energy exchange across different regions of space presents further challenges, given the vastness of the universe and its evolution over time. These anomalies pose significant challenges for cosmology and the academic community at large. When theories fail to account for observed inconsistencies, two approaches emerge: either refine existing theories or consider alternative explanations. The theory of inflation arose as the most promising theoretical framework for extending the Big Bang perspective. Inflation proposes a starting point of rapid expansion, smoothing the universe and endowing it with uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. Notably, inflation's predictions align with observed patterns and variations, reinforcing its validity. While alternatives exist, inflation's scientific influence remains unmatched. Despite past contributions to general relativity and singularities, Roger Penrose's work, particularly his collaboration with Stephen Hawking, failed to match the success of inflation in explaining the universe's earliest moments. Recently, there has been concerted effort to undermine the validity of inflation theory, instead advocating for conformal cyclic cosmology, which is inherently flawed from a scientific standpoint. The key distinction lies in their predictions. Conformal cyclic cosmology posits that remnants from a universe preceding the Big Bang are embedded in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory maintains that the point where inflation ends and a hot Big Bang begins should be causally disconnected from any pre-Big Bang region. Every aspect of our universe exhibits unique characteristics, suggesting that we should rely on the physical universe to reveal what is true rather than solely depending on speculation. In light of early revelations, cosmologists swiftly recognized anomalies in the images sent back by the James Webb Space Telescope starting in 2022. These discoveries may necessitate a reassessment of crucial elements of the universe's origins and evolution. One significant revelation made by the Webb telescope was the existence of fully formed galaxies much earlier than anticipated by the standard model of cosmology. This anomaly challenges the established sequence of events post-Big Bang, where stars and black holes formed first, followed by the evolution of galaxies. Such revelations disrupt our understanding, much like encountering grandparents depicted as children in a story. Moreover, recent evidence has unveiled discrepancies within the foundational theories of the universe, such as the persistent inconsistency in determining the Hubble constant, which endures despite improvements in data accuracy and collection methods. Furthermore, new data from the Webb telescope adds to existing challenges to the current cosmological model. These issues highlight flaws within the model itself, prompting questions among astronomers and physicists. While the model has undergone revisions over the years to align with emerging data, some argue that these changes have been too convenient. Thus, there is growing recognition that a paradigm shift may be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a victory of human knowledge, emerged from Edwin Hubble's momentous discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin, portraying the early universe as a hot, dense soup of subatomic particles gradually cooling over time. However, Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The theory of inflation, proposed in 1981, was introduced to resolve inconsistencies in earlier Big Bang models, further underscoring the dynamic nature of cosmological theory. According to this hypothesis, the early universe underwent rapid extraordinary expansion for a brief period following the Big Bang. While certain issues are addressed by this concept, new challenges emerge, especially regarding the prevailing belief in the existence of one universe, as well as potentially countless others beyond our own. The implications of these findings from the James Webb Space Telescope challenge our foundational understanding of cosmology and the very nature of the universe. The detection of mature galaxies existing much earlier than the conventional timeline suggests a more complex and rapid formation process than previously imagined. This anomaly raises questions about the mechanisms of galaxy formation and evolution, prompting a re-evaluation of the parameters set by the standard cosmological model. Moreover, these observations may point to the influence of physical processes that have yet to be fully understood. For instance, the role of dark matter and dark energy in shaping the universe's architecture could be far more intricate than current theories suggest. With the Webb telescope providing unprecedented detail, researchers are now tasked with integrating these new findings into existing frameworks or, alternatively, developing new models that better account for the evidence at hand. Another area of focus is the reconciliation of the Hubble constant discrepancies. Variations in measurements from different methods, such as those derived from the cosmic microwave background versus those obtained through supernova observations, highlight fundamental issues in our understanding of the universe's expansion rate. These discrepancies may not only reflect measurement errors, but could also indicate new physics, suggesting that our comprehension of cosmic expansion is incomplete. As astronomers explore these anomalies, they must also consider the potential existence of multiverses. If our universe is merely one of many, each with its own unique physical laws and constants, the implications for cosmology and fundamental physics are staggering. The possibility of alternate universes could provide explanations for some of the unexplained phenomena observed in our own universe, fostering a deeper investigation into the nature of reality itself. The ongoing debate between proponents of inflationary theory and alternative cosmological models underscores the dynamic nature of scientific inquiry. While inflation remains a robust framework explaining many observed phenomena, the emergence of competing theories, such as cyclic models, indicates a vibrant discourse aimed at reconciling the intricacies of the universe's origins. As we continue to push the boundaries of our knowledge through advanced observational techniques, we are reminded that our understanding of the cosmos is still evolving. Each new discovery raises further questions, inviting a re-examination of the very principles that underpin our understanding of space, time, and existence. In conclusion, the revelations from the James Webb Space Telescope mark a pivotal moment in cosmology. They challenge established theories and open the door to new possibilities. The journey of discovery is far from over, as scientists strive to unravel the mysteries of the universe and confront the profound implications of what lies beyond our current understanding. This ongoing quest not only enhances our grasp of the cosmos, but also deepens our appreciation of the complexities of existence itself, reminding us that in the grand scheme of the universe, we are still just beginning to understand our place within it.